Thanks for the introduction. My name is Andreas Frölich. I'm the CEO and founder of Horizon Microtechnologies. We are a startup out of Karlsruhe, Germany. And as the title and the introduction said, we are working on making electronics components, especially components for RF applications, by 3D printing and coating technologies. So I would like, before going into a little bit of details on the company itself, I would like to first sort of motivate, since probably most of us don't know us, most of you don't know us from beforehand. I want to motivate why we do what we do before going into who we are. Sort of starts with the manufacturability question. So assume you have a design such as this one, containing a set of a couple of hundred vias here, which you would like to get manufactured, and in the end you want those to be conductive traces. Then the question arises, how do you get this multi-material object where you have conductors separated densely and in high aspect ratio features at very small size. These vias are designed to be 2 millimeters long and 200 microns wide only. So you could 3D print this nowadays. It's rather precise. It's repeatable, and it's not the slow process that it used to be 10 years ago. But then you have a plastic body. It doesn't fulfill your function. However, if you manage to metallize the insides of the vias, you have conductive traces. And so that's where the hybrid in the title of my talk comes from. We use we make parts that have a hybrid composition and start with 3D printing. So how do we do that, or what kind of coatings can we apply? So the process always starts with a prefabricated substrate, which can be 3D print but doesn't have to be. We have successfully worked with ceramics as well, or with customer consigned part made from other plastics. And to those we can apply, on one hand, a protective coating, which is a hermetically sealed and tight coating to prevent attack from the environment to the underlying part, or also vice versa, to prevent, for example, the plastic leaching out into a solution that is being processed by things such as a nozzle or a channel and so on. We have in our portfolio a process called HMT conductive, which applies a thin, transparent conductive layer to virtually any part geometry. This is a conductive but resistive layer, which has its own use in sensor applications, for example, if you need to build a capacitance. And then the one that I will be focusing most on today and here is the HMT metal process, which applies a metallic layer, at the moment copper and or silver. This process is less part geometry agnostic, but still capable of metallizing the insides of tubes to up to a certain aspect ratio and reaching undercuts and so on. This is especially interesting whenever you need to relay signals, such as in telecommunications or RF applications, antennas namely, or if you need to conduct higher amounts of currents. So what's the added value of this approach? We sort of try to map this, and the map is empty here, but we sort of conceptually here we have a layout of options you might find when you assess different manufacturing technologies in terms of their geometrical precision. They will also impact the material of what your machining step will be. And then we have the y-axis, where you can add different engineering relevant parameters, such as conductivity, such as a barrier to the environment, potentially change the tribological properties of your part. And if you look at this, for the case of 3D printing and conductivity, which is why we're here today, you will see that if you look into the 3D printing landscape, there's on one hand technologies which span the whole range of precision, and there's also technologies which give you high conductivity, such as bulk metal printing, but you can't have both at the same time. However, by starting with a template or a substrate made with one of these technologies and then applying the coatings, you can bring it into the top right corner, which is mostly unserved